Okay, this is AP Podcast 6.2, and we're going to talk about integrated rate laws. So, to review what we've been talking about so far, differential rate laws. Differential rate laws are also just called the rate law. And what we do is we see how the rate changes with a change in concentration. So, how does rate depend on the concentration of our reactants? With the integrated rate laws, we're going to see how concentration changes over time. So what happens to that concentration? How quickly does it change? All of those things we can find in the integrated rate laws. So also, to review then, differential rate laws. If we wanted to write the rate and the rate law for this reaction, and this is a decomposition reaction, we have our single reactant going to our products. What we would do is we could say that the rate is equal to negative change in A, and A is the reactant, over the change in time. If we did that calculation, we could calculate the rate. We also know the rate law, which is the rate constant times the concentration of A to some power. So this is everything that we've talked about so far. We're going to add to this today. The first type of integrated rate law we're going to talk about is a first order rate law. So the first order rate laws are the most common by far. If they're asking you to determine whether it's a first, second, or zero order, you should always try for the first order before anything else, because that tends to be the answer. But anyway, it's the most common. This is our general reaction that we've been using, and if we were to write the rate law, this is what it would look like. Rate equals K times the concentration of A, and there is a 1 here that we can't see because it's a first order. This means if the concentration of A were doubled, the rate would also double. So they do the same thing. If we quadruple the concentration, the rate's going to be quadrupled. What they do, though, is they take that differential rate law or that rate law and they integrate it using calculus. And what they end up with is this expression right here for first order rate laws. And I'm not going to show you how they integrate it. You just need to know that this is what they end up with. So we have the natural log of A, and this natural log of A is the concentration of A at any given time. Whatever we set time to be, this is what the concentration of that reactant will be. Plus, this is the natural log of A naught, or A sub 0. What that means then is this is the initial concentration, because this is the concentration of A at time 0 when we first begin. So you can see how we're able to use these integrated rate laws to calculate the concentration of these reactants at any given time. Because if we know the rate constant, we can plug in any time and we can figure out what is the concentration at whatever time we're looking at. So there it is again. The integrated rate laws are always written in y equals mx plus b form. So we have the y equals mx plus b. What that means then is that our slope of our graph, if we were to graph it, and for a first order reaction, the natural log of A versus time is going to give us a straight line. If we find the slope of that line, then that will be the value of negative K. So we can actually find the rate constant using the slope of the graph when we graph these. So that's the first order. If you wanted to look at it, this is what's in the next picture. So say we had a first order reaction and we were plotting these different things. You don't know what these are yet, but this is the one we are looking at. If we have the natural log of A versus time, that tells us it's a first order. If it comes out in a straight line, this is what we use for a second order. We look to see if it comes out in a straight line for 1 over the concentration. That tells us it's a second order reaction. And then if it's just concentration versus time, that gives us a straight line. We know that's a 0 order. But this is the one we're focusing on right now. You can see how I take the concentrations over time. If I plug it into this, it gives me a curved line. If I plug it into this one, I get a curved line. But when I plug my concentrations in my time into the natural log of A versus time, that's when I end up with the straight line, and that's what cues me in that this is a first order reaction. And again, we can see that the slope, the negative slope, is equal to the rate constant. So the time required for a reactant to reach half its original concentration is called the half-life of the reactant. For a first order reaction, the half-life equation is half-life is equal to 0.693 over K. And this should look familiar from when we did our nuclear chemistry extra credit assignment, because this is the same half-life equation that we used there. This can also be rewritten though if you want to know like where did this 0.693 come from. What they did is if you have the natural log of the concentration of A at time 0 and then the concentration of A at some time equals KT. This is what it looked like originally, but if you think of half-life, if I originally had 2, that means half of this would be 1 at the half-life. It's when half of it disappears. The natural log of 2, which is what this here would be, gives us 0.693. So right here we have the natural log of 2 gives us 0.693, which is why we're able to shortcut it into this formula right here. So that's the half-life equation you use if you're dealing with a first order reaction. All right, second order rate laws. Here's our general reaction again. That means if we write the rate law, it's rate equals the rate constant times the concentration squared. So if we double the concentration, we're going to quadruple the rate. And if we triple this, it's going to go 6 times faster. So the integrated second order rate law looks like this. We have 1 over the concentration of A equals KT plus 1 over the original concentration of A. So that's your second order rate law form. It looks different because we're not using natural log this time. And here it is. The slope is equal to K this time because this is still written in y equals mx plus b form. This time the slope is equal to K. So in order to get our second order reaction in our graph of a straight line, we're going to take 1 over the concentration versus time. That's my y and that's my x. So when I do that and it's a second order, it's going to give me a straight line. Here's our 3 graphs again, and we can see that when we plug it in, so again this is our second order, first order, and our 0 order. If we take all those concentrations that we have versus the time and we try to plug them into here, it's not going to give us a straight line. If we try to plug it into the natural log of A versus time, it's not going to give us a straight line. We're only going to get a straight line if we plug it into the 1 over the concentration of A versus time. And here we can see that the slope is equal to K. So whether it's a first, a second, or a 0 order will determine which of these 3 graphs you get as a straight line. The half-life expression for a second order equation looks like this. And you can just plug in the original concentration that you had at time 0, multiply it by the rate constant, and that will tell you what the half-life is for these reactions. The last one is a 0 order rate law. And a 0 order rate law means that no matter how I change the concentration of my reactant, the rate stays the same. So the rate will remain constant, it does not change with concentration. Anything to the 0 power is 1, so it's just that the rate is equal to K. The integrated 0 order rate law looks like this. The concentration is equal to negative KT plus the original concentration. And then when I put it in or if I look at the y equals mx plus b form, which is what we just had on that last page also, then we can see that the slope is negative K in this one. The 0 order reaction, if we have it, if you plot the concentration versus time, that's when you're going to get a straight line. And we'll look at a set of 3 graphs again so you can see that. This time for our 0 order, we get the straight line because that's what it is. Our first order is curved and our second order is curved. So depending on what they are, will determine what sort of straight line you get. Okay, the half-life expression when we're talking about 0 order rate laws is the original concentration over 2 times the rate constant. So you can plug all that information in and you're able to find the half-life for your reactions. There's a really good graph or chart right here that summarizes everything that we went through really quickly. But really what you need to know is we take the differential rate laws and we integrate them, and that's how we end up with these integrated rate laws. So here's your zero order, first order, second order. These are the ones that we were dealing with first. They get integrated and then they become these right here, which are right below them. It tells you what gives you a straight line for each one, what the slope is equal to, and also what the half-life equation is for each. So this is a really handy chart to use until you kind of get the hang of what everything is. We're going to do 3 practice problems together. So the first practice problem, I have dinitrogen pentoxide, and it's going into nitrogen dioxide and oxygen, was experimentally determined to be a first order reaction. So that is really important. I'm going to underline that so I don't forget it. Use the following data to calculate the concentration of the reactant 150 seconds after the start of the reaction. So we wouldn't be able to do this with the differential rate laws because they deal nothing with time. With the integrated rate laws, though, we're able to deal with time and figure out the concentration as time goes on. So using this information, and they gave me the rate constant right here, what we're going to do is we're going to use the integrated rate law for a first order reaction, and we're going to solve for the concentration after 150 seconds has gone by. It is very tempting if you look here. Here's 100 seconds, and here's 200 seconds. So there's the 100, there's the 200. It's really tempting to assume that at 150 seconds, right in the middle here, my concentration would also fall right in the middle. It'll be close, but that's not true. You can't just base it off of its position on this chart and what it looks like it should be. You really do need to calculate it. So on the next page, here I have that data again. What I'm going to do is I'll write the integrated rate law, and this time we'll use the N2O5 since that's what we're solving for, negative KT plus the natural log of its original concentration. So here's the integrated rate law that we're going to use, and we just plug in. This is what we're solving for right here. That's our x, that's our unknown. So we have natural log of the N2O5, that's my x, is equal to negative. And I know from the problem, from what they gave me, this is 6.93 times 10 to the negative third. They said it was per second, so I'll write it like that. And then I want to know at time 150 seconds what's the concentration, plus the natural log of 0.1000, and I pulled that as the original concentration right here. So I take this, I plug all that into my calculator, and I end up with the natural log of my unknown, or of my reactant there, is equal to negative 3.3421. So I multiplied those together, I punched in natural log of 0.1, and then I added up those two answers and I got this. In order to solve for the concentration of N2O5, you have to do the anti-log or the anti-natural log. But if you look at your natural log button, you should see e to the x above it. So if you hit shift in that or second in that button, you should get this. What you're going to do then is I'm going to write it up here. You would punch in e to the negative 3.3421. That answer is what this concentration is. And that equals, I'm going to run out of room, 0.0354 molar. And I'm going to stop for a second and double check that that makes sense with what I was looking at on my table. That does fall in between these two values here, so it does make sense that this is a reasonable answer. So your final answer altogether is this one right here. So after 150 seconds, that's the concentration of my reactant. Okay, practice problem number 2 says, a certain first order reaction has a half-life of 20 minutes. So again, First order reaction, half-life. If we think back to what the half-life was, we had nope, that's not right. Yes. Ooh, going crazy. Half-life is equal to 0.693 K. And I'm going to use this, but they're asking me to calculate the rate constant, which is K, so I'm going to rearrange this. K is going to be equal to then 0.693 divided by the half-life. That is a half. That is equal to 0.693, and they gave me 20 minutes. So I'm going to plug that in on the bottom. It doesn't have to be in seconds unless they specify the unit of time. So since they didn't, I'm going to leave it in minutes. K then, K not T, is going to end up being 3.47 times 10 to the negative second. And that's going to be per minute. And I better put MIN. So that's the value of my rate constant right there. There is a second part to this question. It says how much time is required for this reaction to be completed, to be 75% completed. So if I stop for a second, I'm going to assume, let's just think 100. It could be 100 grams, 100 moles. If I have 100 grams to start with, if it's 75% completed, that means 75% of it is gone. And that means I have 25 grams remaining. This is important for setting up my ratio. So if I started with 100, I should have 25 remaining. I need that because when I plug this in to our half-life equation, and in this one I need to use where we have the actual concentrations because I need to plug in a ratio to solve for T. So what I'm going to do is, originally I'm going to say I have 100. It doesn't matter if I'm thinking grams. This is molarity, so I could think moles, molar there, whatever you want. So I'm going to have natural log of, I had 100 to start with. I only have 25 remaining. That's equal to, I already calculated my K value, my rate constant. And that's minutes. And then I have my T out here, which is what I'm solving for. So when I do all of this math, I end up finding that it takes about 40 minutes for the reaction to be 75% complete. And that's how you can use those half-life equations to manipulate or to find out concentrations after a set amount of time, how much will I have left, and things like that. All right, our last question here I'm going to try and use Excel for. So let's see if I can get it. All right, so here's our question. It's kind of tiny. I'll try to zoom in for you, but it says, it gives us all this information and it tells us that this data was collected right here, and this is on your paper. We have three parts. Is this reaction first order or second order? Then what is the value of the rate constant for the reaction? And then C is what is the half-life for the reaction under the conditions of this experiment. So the first thing I'm going to do is I'm going to solve for this reaction being a first order or second order. I like to use Excel with this because it allows me to graph on Excel, which is a lot faster than trying to do it all by hand. So when we're doing these homework problems, if you have access to this, you are more than welcome to use it. So what I'm going to do with A, I wrote the original information from the question, I just recopied it right here. So I took this chart and I recopied it. What I know is if it's a first order, the natural log of the reactant versus time is what should give me a straight line. If it's a second order, 1 over the concentration versus time should give me a straight line. So the first thing I need to do is I need to get this converted. So I go equals natural log, and then I'm going to click on the concentration because I need the natural log of that concentration, and it converts it for me. So I'm going to click there, and if I drag that little square down, it's going to copy the equation, the formula for each of these cells. And then the time doesn't change. So I'm just going to copy and I'm going to paste it in right here because the time, there's no difference. Time is still time. And then I'm just going to go ahead and get this one done as well. So this is going to equal 1 divided by, that is the wrong divided by, my concentration again. And if I click enter, it does it for me. Again, I'm going to drag that little square down and let it copy the formula all the way down for me. And my time, I need again. So I'm going to copy. I'm going to paste it into this chart, possibly. All right. So now if it's a first order, I have that information. If it's a second order, I have that information. So what I'm going to do is I'm just going to highlight the natural log values right here. You want to do a scatter plot, and I just don't connect it. This is what it ends up looking like, and it's a little weird with the natural logs because they're negative. It wants to put the y up top, which is fine. It's not a big deal. You can tell though that this y is not the same as the time that I have here. So what I'm going to do is I'm going to change that. I'm going to select the data that I want. For the x values, I come back to the chart and I can highlight that those are what I want for the times. And then I'm going to go ahead and just put natural log of, and I'm just going to call it A versus time, just so I can remember what it was. So there's my natural log of A versus time. This is kind of curved. It doesn't look like a straight line. So I'm going to keep going on to my second order here. So highlight again, scatter. This looks great. This is a straight line and this is what I wanted. So I have here my second order graph. Again, the time part didn't get carried in like I wanted it to, so I'm going to select it just like I did the other one. Highlight that. And I'm going to call this 1 over the concentration of A versus time. So I can tell by looking at this graph, this is a straight line, this is kind of curved. So what that tells me, is this reaction first order or second order? Well, that tells me that the answer to that is it's a second order, because that is the one that gave me the straight line. So second order reaction, here's what we got. What is the value of the rate constant for the reaction? With a second order reaction, we said that K is equal to the slope of the line. So if I look here and I'm in Excel or some other graphing thing, what I can do is I can add a trend line. And when I add a trend line, I have the option of displaying the equation on the chart, and I click OK. By displaying the equation on the chart, when I zoom in here, we have y equals mx plus b form, and there's my slope. It's 0.0612. So I know right away there is my rate constant. I have it. It's for me. I didn't have to do any calculations. Let me see if I can do this, if it will let me write on here. Oh, it's not going to be very easy to see, but we'll try it anyway. If you had wanted to do that by hand, though, you would go slope. Wow. Let's try again. You would go slope is equal to the change in y over the change in x. And you could just pick 2 points. So say you wanted to pick the first and the last point, you could pick those 2 points and those 2 points. And if you plug that in, you're going to end up with a little bit of a different value, so 0.0615, which is slightly different from that, but it's pretty close. You may have to do it this way in order to figure out units, but those would be the units. And you would have to plug in, if you couldn't remember, like you would have to do this, how we did in the homework, and figure out what the units are, so you would know what this 0.0612's units were when you went to use them. But you can either solve it by hand, doing change in y over change in x, or you can use the program that you're in for graphing and it'll just pop up and tell you what K is right there. So that's solving for K. That's the value of the rate constant for the reaction. The last question that they're giving us is, what is the half-life for the reaction under the conditions of the experiment? Well, what they've told us so far is that we found out that it's a half-life that has a second order for a reaction. So we would go back and we know then if it's a second order, its half-life equation is 1 over the rate constant times the original concentration. And all we need to do is just plug in that information. I'll just use the 1.5 for if you were to calculate it by hand. And then the original concentration is right there, 0.01. And when I plug that in and get my answer, I find out that it's around 1,626 seconds for the half-life. So recapping what we did. First or second order, the only way to really do that is to plot it. So we plotted the first order for the natural log. The second order, we plotted 1 over the concentration. We looked for which one gave us the straight line, which was the second order equation. It's the one that produced the straight line. For the value of the rate constant, you can either do the trend line on Excel and then add the equation, or you can do the change in y over the change in x and you can solve for it that way. And then for part C, what is the half-life? We just use the formula that we know for second orders. That's the half-life for the second order reactions, and we solved for what it was. So these do take time because you have to plot them, but having Excel does make it go a little bit faster. All right, and that is the end of the podcast. So we're going to do some practice with these in class. We'll try to get some computers around so that if you guys want to use Excel and graph your problems, that makes it go a little quicker. Plus, it's good practice on how to use Excel. So we'll talk about these in class, but it's a good thing to go back and look at that chart that summarizes everything because that's really what you're going to have to know for the test.